All right. So, as appeared on Twitter there yesterday morning. Okay, your quiz goes as follows: list the points of the atomic theory. All right. So, if they have something along these lines for the points, okay, you can give them 1 mark each. If they have everything is made up of atoms, okay, something along those lines, everything made of tiny indivisible particles. If they wrote it out word for word, that's fine too. Okay, but if they have a point there that says something about being made of atoms. Okay, that'll be 1 mark. Okay. Second point. Anybody got it? Right. Okay. Atoms of the same element are identical, okay, or atoms of different elements are different, or atoms are unique to each element, something that implies they understood that each atom or each element has its own atoms. Okay. Oh yeah, it doesn't have to be in this order. No. Okay. Third point. Okay, atoms can join together in simple whole number ratios to form compounds. So if they have something about atoms joining to form compounds and something about whole number ratios, all right, you can give them a mark. All right, so something about whole number ratios and atoms forming compounds is good enough. Okay, and lastly, okay, you could summarize the last point something like this. Atoms are not changed in a chemical reaction. All right, they may have written something like atoms can be separated, joined, or rearranged, but cannot be turned into other atoms, or something along those lines. As long as they have something there that indicates they understand you cannot change one atom into another atom by a chemical reaction, they're good enough. Okay. By the way, RxN is shorthand for reaction. If you ever want to save yourself some time writing notes, RxN is shorthand for reaction. Ah, good enough. Good enough. Yeah. All right. Any other questions on number 1? All right. Like I said, on a unit exam, something like that, how will I test this? Written response or multiple choice? Multiple choice. Right. Number 2, who devised this theory? Right, John Dalton. Okay, 1 mark. Name and describe the particles in an atom. All right, so very simply, we've got proton, positive, nucleus. 1 mark. Okay, neutron. I always spell neutron wrong. It never looks right. Neutron, neutral. I always spell neutral wrong too because it never looks right. Okay, nucleus. I never spell nucleus wrong. It always looks right. Okay, and electron. Okay, negative. Okay, and I'll accept cloud or around the atom or outside or something like that. Yeah, orbits. Something indicating it isn't in the nucleus. All right, 1 mark each. All right, so 1 mark if they got all the stuff for proton correct. 1 mark if they got all the stuff for neutron correct. 1 mark if they got all the stuff for electron correct. No half marks. Okay. Number 4, which particle did J.J. Thompson discover? Right, he was the plum pudding guy, so electron. Okay, 1 mark for that. Okay, for the following compound, give the proper formula. Since we only went over ionic compounds on Friday, both of these obviously are ionic. I couldn't fairly ask you something about a molecular compound. So if we got calcium, we write Ca, okay, and it is always a 2+ charge. Chlorine is always a -1 charge. What do we do with these? Drop and swap. CaCl2 is all they had to write. They don't have to show any work. Okay, it's 1 mark. And the name for the compound below, we've got sodium and oxygen. It's an ionic compound. Do I write any prefixes for that too? No. So it's just sodium oxide. No capital letters. I'll let it go today if they capitalized it. All right. So whole thing is out of 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. 11. Okay. So give him a mark out of 11. Okay, let him see it, and then please hand it into the box, top one, at the back table there. All right, quick review of what we were going over on Friday. All right, for ionic compounds, when we're naming them, we simply write the metal first and the nonmetal second, and the nonmetal's name always ends in "ide." Right, okay? We don't put in any prefixes because we know, because of the balancing of charges, there's only one way that those two elements can go together when they form an ionic compound. So there is no need to put in any prefixes. All right. When we are writing the name for trickier ones, that is the ones that involve those multivalent metals that have more than one possible charge, all right, which element do we look to help us figure out the charge? Right, okay? We always look to the nonmetal because there are no multivalent nonmetals. Every single nonmetal on your periodic table there has only one charge. Okay, so we can figure out from there what the charge on the metal is. So I don't think we got all the way through these on Friday, did we? Okay, what did we get to? Number 5? Number 7? Okay, so let's look at number 8. Okay, so we've got antimony and sulfur together here. Sulfur's charge is always -2. So how many negatives do I have in total if there are 3 of those? How many? 6. 3 times -2 is 6, right? Everyone follow me there? Always multiply the number of atoms by the charge. Okay, so we've got in total 6 negatives. I have to have how many positives? 6. All right, I've only got 2 antimonies with which to do that. So what's the charge on antimony? 3. Okay, +3. So when we name this, it will be antimony 1, 2, 3. Okay, Roman numeral 3, sulfide. Okay, is that ringing a bell? All right, looking at number 9, I've got nickel and I've got nitrogen together. Okay, nickel's 2 possible charges are 2 and 3, yes? Is that right? Yeah, 2 and 3. All right, so what I need to do then is look at nitrogen. Nitrogen's charge is always -3. So there are in total 6 negative charges here. I have to have 6 positive charges because all ionic compounds come out to a net charge of 0, which means every one of these nickel atoms has a charge of 2. So when we write the name, it is nickel, Roman numeral 2, nitride. Okay, and then for number 10, we have ruthenium and oxygen. Okay, ruthenium's possible charges are 3 and 4. So every oxygen is -2. How many negatives in total here? 4. 2 times -2 is -4. All right, there's only one ruthenium, so it has to be +4, right? Okay, if 2 times -2 is -4, I have to have +4, and I only have one atom with which to do it. So its charge has to be 4. Ruthenium, okay, IV, oxide. All right. Like I say, those don't come up that often, all right? But I usually put, I put 1 maybe on a quiz, 1 or 2 on a unit exam, okay, things like that, so that you do have to do it. All right. Now, last thing that could possibly come up before we get to molecular compounds. If you look at the top of your periodic table, you see the table of common polyatomic ions. Yours looks a little different than mine, but something like this. Okay, table of common polyatomic ions. These are ions that they're two elements, two or more elements, already bonded together. But they're bonded together and their electrons, their charges don't balance, so they still have a charge together. All right? When you're putting them with another element, usually a metal, you treat them as though they were any other non-metal element. Okay? So if, for example, I have, let's say, sodium and nitrate together. Okay? Nitrate is NO3, and it has a -1 charge. All right, so if I am looking at that, so let's say I have sodium, sodium nitrate. Okay, sodium's always +1. Okay, nitrate's always -1. So is this okay, dropped and swapped? Yeah. Okay. All right. What would this compound be called? Nope. Sodium nitride is this stuff. Na3N. Okay. The only thing that changes for naming a compound that has a polyatomic ion in it is you don't end it in "ide." You leave it however it appears on that chart. So this stuff is sodium nitrate. All right. They've already been given an ionic name in that table of polyatomic ions. So this stuff is sodium nitrate. All right. Okay, so everything sort of remains the same except for that "ide" thing, which is probably the easiest thing to have changed. All right, dropping and swapping remains the same as well. So let's say I have something like this: calcium hydroxide. Okay, formula for calcium is Ca, and calcium's always a 2+ charge. What's the formula for hydroxide? OH. All right. And it is a -1. So when I drop and swap, what do I have to do here? Right? Okay, so if I write this, that tells me I have 1 calcium atom. How many oxygen atoms? 1. And how many hydrogen atoms? 2. Is that what I want to communicate? I'm supposed to have how many hydroxide ions here? 2. That means, it's just like math. If I want this 2 to apply to everything, I put it in brackets. All right? So if you have to swap and drop a polyatomic ion and you need more than one of it, you just put it in brackets. And then everyone knows that that 2 or 3 or 5 or whatever it is you had to put out there applies to the whole ion instead of just the last bit. Okay? That makes sense to everybody? All right. We'll work on a few of those in a bit, but just so you have the idea of how it works. It's exactly the same as naming, okay, or as writing the formula for something else except for the brackets and the "ide." Okay? It's the only thing that's different. All right. Molecular compounds. So, molecular compounds happen when two nonmetals react to form a new substance. Okay? Nonmetals are usually negatively charged. So is there any way for them to balance their charges? If they're both negative, can I get to neutral if I keep adding negatives? No. Okay? So there's no way to balance the charges. So what they do instead is they share the electrons. All right? It's what we call a covalent bond. They share a valence or outside electron. All right? So they're cooperating, covalent. They're sharing that electron. That is actually far more stable than an ionic bond, which is why many of your molecular compounds are actually not soluble in water. Okay? They don't dissociate. That means split into charged particles when they hit the water. They stay together and oftentimes don't dissolve. Now, that's not a hard and fast rule. There are some molecular compounds that are highly soluble in water, like sugar. Okay? Dissolves pretty easily in water. All right? But other molecular compounds would be things like oil, butter, any kind of fats are all molecular compounds. Ammonia, okay, dissolves in water, right? It's a molecular compound, so it would be an exception, right? And some other ones, but they generally are less soluble than their ionic counterparts. Okay, so if we're looking at a water molecule here as an example, okay, the hydrogen atom has one proton and it has one electron. So let's say that, just for argument's sake, this electron here belongs to hydrogen and the red one belongs to the oxygen. All right? So they are sharing them. That gives how many electrons to oxygen in its outside shell? 8. Is that how many it wants to have? Yeah, its outer shell is full. All right? That first inner shell can only hold how many electrons? 2. Is hydrogen happy? Yeah, its outer shell also has 2 electrons. Sort of. They're sharing it, but they're both reasonably happy because both of their shells are sort of full. Now, I want you to get the idea that this sharing is always equal. All right? It isn't always equal, especially in an example like water. All right? Water is a special molecule. We'll talk about it later in the unit. It's called a polar molecule. Polar meaning oxygen's greedy and actually gets to share the electrons more often. All right? It's what we call more electronegative. So the electrons stick around here and they stay closer to oxygen than hydrogen. What it ends up doing is, since this proton here that's all by itself is kind of exposed, this end of the molecule ends up being positive. This end of the molecule ends up being negative. And as a result, water can do all kinds of really cool things that most other molecular compounds don't do, like surface tension. It can expand when it freezes, okay, stuff like that that most things don't do. Right? That's all because water's a polar molecule. All right, so this is your ionic bond. Okay, the electrons get traded. Okay, this would be your covalent or molecular bond. The electrons get shared. That's much more stable. They have to stay together in order to keep their shells full. Okay, questions there? All right. All right, naming molecular compounds. Okay, so molecular compounds arise when 2 or more nonmetals react to form this new substance. Okay, they're shared, the electrons are shared. The difference between naming them, though, is that this sharing could result in any number of combinations of 2 elements. All right, for example, when nitrogen and oxygen go together, they can form this, they can form this, they can form this. All right, they can form any number of compounds because they're sharing their electrons, and whatever way will get both of their shells full will work. Okay, so we have to be able to communicate to people which combination of nitrogen and oxygen we're dealing with, and how do we do that? Not suffixes, prefixes, right? They come before. All right, so this is why we put in the prefixes. This stuff here would be or this would be nitrogen dioxide. This would be dinitrogen trioxide. This would be dioxide, right? So on and so on. So we always put in prefixes so that people know which combination we're dealing with. John. Yeah. That is nitrogen dioxide. This one here? Oh, this one here. This is dinitrogen monoxide. It should say monoxide there. That's a typo. Now, when you have 2 vowels together, you can write it, typically people just write it as monoxide, but you could also write it as mono-oxide. I believe both are grammatically correct. I'll accept them because I think they both look fine. Okay? All right. So other examples here, we've got carbon with sulfur, we've got carbon disulfide, okay? And for a big example, you've got 4 phosphorus and 10 oxygens. That would be tetraphosphorus decaoxide. I'm never going to ask you to remember the prefixes beyond 10, all right? In case you need to remember the prefixes, okay? 1 is mono, 2 is di, 3 is tri, 4 is tetra, 5 is penta, 6 is hexa, 7 is septa, or hepta. If you take Mr. Reel's class next semester, hepta, he hates septa. Don't use it. Okay, number 8, octa. Okay, number 9, nona. and 10 is deca. Okay, and something else you may see here in this diagram is on the top you see the molecular forms of some of the elements. Okay? Some of the elements on the periodic table are what we call molecular elements because they'll actually bond with themselves in pairs, in quads, and sometimes even in sets of 8. All right? They're special. We have to recognize these special elements because when we get to reactions, if they ever end up by themselves, we have to remember that oxygen, when it's by itself, is always how many? 2. It's always O2, right? You never see oxygen by itself. Occasionally, you see it as O3, which is now ozone. Okay, ozone is O3, but it's pretty rare. All right. So some of the elements will bond with themselves to form a pair of atoms. Okay, those are the molecular elements. We'll just quickly go over those, and you can highlight them on your periodic table. All right, so your molecular elements are nitrogen, oxygen, oh, all right, I'm just going to undo all that, guys, because it's just making a mess. All right, so we got nitrogen, we got oxygen, okay, fluorine, everything under fluorine. So fluorine, chlorine, okay, bromine, iodine, astatine, okay, and hydrogen, oddly enough. Everything that's highlighted in yellow is a pair. Okay, when they bond with themselves and form a molecular element, they come as H2O2, N2. Okay, always come as a pair of atoms. All right, there are a couple of special ones. Okay. One of the special ones is phosphorus. Okay, phosphorus comes as a 4. The other special one is sulfur. Sulfur always comes as an 8. Whoa. Okay, so that's the way it's set up. All right, so nitrogen, oxygen, fluorine, chlorine, bromine, iodine, astatine, and hydrogen are all 2s. Phosphorus is a set of 4, and sulfur is a set of 8. All right. What we usually do is say all the twins, the phosphorus quadruplets, and the sulfur octuplets. All right, and you can remember them. There's some rhyme, but I can never remember what it is about this story that you tell, and it has to go with all of them, or there's a word, or what do they call those, an anagram, or whatever it is that you can make up. I don't know. You can figure it out for yourself. Okay, just highlight them on there, and you'll have them. Phosphorus is sets of 4, so they're the quadruplets. Okay, and sulfur are the octuplets. Always comes as S8. Okay, so when phosphorus is by itself, it comes as P4. When sulfur comes by itself, it comes as S8. All right, not in compounds, only when it's by itself. All right. So, like we said, rules are you write the names in the order in which they appear in the compound. So if carbon appears first, we write carbon first. We write sulfur second, and whatever one is second ends in "-ide". Okay? We don't change the first one to "-ide", just the second one. It always ends in "-ide". Okay. The other rule we have to remember. How many carbons are there here? 1. Do you see a mono on carbon? Okay, but there is one over here on dinitrogen monoxide. You never put a mono on the first one. I don't know. Chemists have to be difficult. They always have to have some rule that makes them feel important. I don't know. Okay, so there's little things you always have to remember. You never put mono on the first element, even if there is only one of it. But you do put all the others on there, so di, tri, and all the others. Hey, anybody need that slide anymore? Okay. I want you guys to try the first 5 on here, then stop. Okay, we'll go through them, then you can do the rest. All right, so on our first one here, we've got 1 nitrogen and 3 iodines. Okay, we don't put mono on the first one, so this is nitrogen triiodide. You don't have to have the hyphen, but I think it's grammatically, you're supposed to have it. Okay, number 2, you got carbon and you've got iodine, so this is going to be carbon tetraiodide. Okay, for number 3, 2 nitrogens, 3 oxygens. We already did this one. What is it? Dinitrogen trioxide. Okay, for number 4, we got tellurium and astatine, so this is going to be tellurium diastatide. Okay, and then for number 5, we got 2 phosphorus and 3 sulfurs, so diphosphorus, okay, trisulfide. And again, remember guys, no capital letters in here. Okay, any questions on the first 5? All right, let's finish those up. I'll give you a couple more minutes and we'll go through the rest. All right, I'll do another 5 here just so you can sort of check how you're doing. All right, for number 6, we've got 1 oxygen, 1 sulfur, so this is oxygen monosulfide. Okay, number 7, we got 3 silicones and 4 phosphorus, so this is trisilicone tetra phosphorus. Sorry, phosphide. Yeah, absolutely. Okay, for number 8, we've got 1 sulfur, 2 chloride, so sulfur dichloride. Number 9, 1 silicone, 4 hydrogens. Hydrogens listed first, acting as a metal or a nonmetal here. Right, has to be because we're doing molecular compounds right now, right? So it's behaving as a non-metal. So this is silicone tetrahydride. And number 10, tetraboron tricarbide. I don't actually know that that compound exists, but it's just an exercise in naming. Probably a lot of those don't actually exist. How many people are done? All 15? Okay. Just quickly do the rest then here. So we got 2 astatines, 3 seleniums. So this is diastatine. Arsenic, sorry. Diarsenic, not astatine. Astatine's AT. Diarsenic. Triselenide, or selenamide, whichever one you want. Okay, number 12, sulfur dibromide. Okay, number 13, dinitrogen trisulfide. Okay, 14, tetraphosphorus octasulfide. And lastly, tellurium dichloride. Okay, questions on any of those guys? Alrighty. Okay, now this one's a mix. Some of these are ionic, some of these are molecular, some have polyatomic ions on them, some of them may even be multivalent metals. Right? It's been kind of easy up to the point because you knew which rules you had to follow for all of them. Right? Now what I want to see is, can you identify, well, this one's ionic, so I apply the ionic rules. This one's molecular, so I apply the molecular rules. Right? That's what we want to see here. All right, so I'm going to give you a few minutes to do these 15. Probably won't take you very long. Right? And then we'll go over them. All right, so we'll have a quick look at these here, guys. So for number 1, it's an ionic compound because it's got a metal in it. All right, so lithium chloride. All right, for number 2, also an ionic compound. Chromium is a metal. Chromium is also a multivalent metal with more than one charge. Okay, fluorine is always -1, and there are 3 of them, so that gives us 3 negative charges, which means that chromium has to be the 3 positive charge. So we have chromium Roman numeral 3 fluoride. Okay, for number 3. Both of these are non-metals, so we are going to be using some prefixes. Phosphorus tribromide. All right, for number 4, zinc is a metal, so we go back to the ionic naming rules, zinc iodide. Okay, number 5, is that an ionic one or molecular? It's molecular. Both silicon and oxygen are non-metals, so this is going to be silicon dioxide. Okay, and number 6, ionic or molecular? Molecular, both are non-metals. Carbon tetrasulfide. Okay, how many people are done to number 10? Okay, so let's go up to number 10 then. All right, number 7 was probably a little tougher to find. Okay, technetium or technetium, I don't even know how you pronounce it. Okay, is a metal. Okay, and we've got 7 iodines with it, so the charge on technetium is 7, but it's only got the one charge. So this is technetium iodide. Okay, and then we have sodium with OH. What's the name of OH? Hydroxide. So this is sodium hydroxide. We'll actually be using this in several of our labs. It's the active ingredient in oven cleaner. If you've ever sprayed oven cleaner, that smell is sodium hydroxide. It is highly basic and would peel the skin off your bones were you to get it on you, which is why it's so good at peeling the crud off the inside of your oven. Okay. All right, number 9, we've got calcium with SO4. All right, if it's in brackets, it means that it is a polyatomic ion. So what's the name of SO4? Sulfate. So this stuff is calcium sulfate. Will you ever use a prefix with a polyatomic ion? Can't be. It's an ion. It's a trick question. Okay? Anytime you have a polyatomic ion, you are dealing with an ionic compound by default. Okay? All right, number 10, we've got potassium with MnO4, which is called what? Polyatomic ion, what's the name of it? Julia? Permanganate, right. This stuff is potassium permanganate. It is a very interesting little material. Little purple crystals. They look very pretty until you touch them. They have a chemical reaction with your skin, the oil actually on your skin, that turns it brown. Not a pleasant brown. A very questionable brown. Don't want to get it on your hands. People will wonder about you. Okay? Yeah. I had a kid when I was like in my second year teaching. Wouldn't listen, wouldn't listen, wouldn't listen. We went and did a lab. We were using this stuff. He's like, Mr. Goodere, can I play with that? After I'd said like several times, please don't touch the potassium permanganate. They used to actually use it as an anti-fungus stuff on feet. It would kill athlete's foot. And like, What did I say earlier? I don't remember. Take your chances then. His fingers were this ugly dark brown, like on the fingertips for like a week. It takes a long time for that to exfoliate away. He listened a lot better after that. Yay, how many people are done to 15? Okay. Number 11, ionic or molecular? Molecular. Okay, so this is nitrogen monoxide. Okay, number 12. Okay, we got a polyatomic ion, so it's obviously an ionic compound. This stuff is beryllium cyanide. Okay, 13 also has cyanide in it, so it's again an ionic compound. This is barium cyanide. Okay, 14, Na Hco3. What's HCO3? Right. What's this stuff? Sodium hydrogen carbonate or sodium bicarbonate. What's the common name for that? Baking soda. Yeah. And obviously I would accept either bicarbonate or hydrogen carbonate. Either one is fine. Okay, and then 15, we have PO4. Now, here's something to watch for. Is PO4 on your table of polyatomic ions? You have PO3? No PO4? Yeah, PO4. All right. So this stuff, if it's in a compound, is called phosphate. All right. If I was to put a metal in front of it, it would be whatever that metal was, phosphate. But if I only write it by itself, is it an ion or is it a compound? It's a compound. I have to name it differently. All right. If this stuff, let's say, was with sodium and it was Na3PO4, this would be sodium phosphate. Since this stuff is by itself, it is phosphorus, okay, tetra oxide. One of those weird rules, okay? Sometimes ions can pick up a stray electron and become a compound by themselves. Okay, questions on any of those? All right, that's what we're going to be working on for the next day or so. I don't think it'll take us much longer than that to kind of get through all the ins and outs of naming. All right, then we're going to move on to that extra lesson that you guys have, okay? All right, now when you're converting chemical names into formulas, just, I mean, we've looked at it, but we haven't done any practice of it, just so you have notes on the steps, okay? The first step in actually writing the correct chemical formula is to decide whether the compound is ionic or molecular, all right? Because if it's ionic, you're going to drop and swap. If it's not, you're just going to use the prefixes to tell you how many of each thing there are. Okay, so for ionic compounds, okay, you write the formula for the metal. So let's say, just as an example, we were given this, let's say. All right, let's say we were given that name and asked to write the formula for that compound. So my first step would be write the formula for the metal and indicate its charge. So I would go Na plus 1. All right, then I would write the formula for the non-metal and indicate its charge, phosphide, minus 3. All right, and then I would balance the charges, okay? And again, for step 4, you might just want to write swap and drop, okay? We call that balancing the charges to make the compound come out to 0. So we put the 3 here, and we put the 1 there, but we don't write 1s. And we've got Na3P, and we're done. Okay. Okay, and then for molecular, it's pretty straightforward. Write the formula for each element. So let's say we were given this as an example. Right, tricarbon octahydride. So I'd write the formula for each element, carbon, hydrogen, and then I look at the prefixes and I put in the right numbers. Tri means 3, octa means 8. What's that stuff? Besides tricarbon octahydride, has a common name. especially important in barbecuing. Propane, yeah, that's propane, C3H8, propane. Alrighty, questions there? We're all good with that? Okay. Alright, so you've got those sheets in front of you. It doesn't really matter which order you do them in. Alright, it's just if you need help on any one of them, you just have to let me know which sheet it's on so I can find it up here on the smartboard. Alright. I would say just work on that here for, well, Belle's going to go here right away. So, not for homework tonight. Please do not do all 4 of those tonight. Okay? We need to have something to do in class tomorrow. Alright? So, you don't have any homework for me tonight. Thursday's quiz, definitely going to be on this stuff though. Alright? So we'll work on it tomorrow in class, and you can work on it tomorrow night if you feel you need more practice.